Convergence of a series with alternating terms and the alternating series test. Objectives. By the end of this lesson, you should be able to define an alternating series, determine if a series is alternating, list the tests for convergence of a series with alternating terms, and use the alternating series test to determine if a series converges. An alternating series is a series in which the terms strictly alternate in sign. In other words, no two consecutive terms have the same sign. Alternating series are often represented by the sum from -1 to the n of a sub n, or the sum from -1 to the n plus 1 of a sub n. Alright, for these first few examples, we want to write out a few terms in the series to show it is alternating. So we have the sum from n equals 0 to infinity of -1 to the n plus 1 over n factorial. So we're just going to go ahead and start by substituting in 0 for n. So we're going to have -1 to the 1 over 0 factorial plus -1. Now if I plug in a 1 here, 1 plus 1 is 2 over, and now I plug in 1 for n, so over 1 factorial, plus then I'll have -1. I'll plug in a 2 for each n, so 2 plus 1 gives me 3 here. And then in the denominator 2 factorial, we'll just go one further. This is going to be -1 to the 4th over, 3 factorial. So we should simplify this. Here, -1 to the 1, so that's going to give me a -1, and 0 factorial by definition was 1, so we have a negative term, plus -1 squared, so if I take a negative to an even power, I'll get a positive value, and then 1 factorial is 1. And then I'll have plus, well, I have -1 cubed, so a negative to an odd power is going to give me a -1, and then 2 factorial is 2. So now I have a negative, a positive, a negative, and so this last one that I'm going to show is -1 to the 4th, so negative to an even power is going to give me a positive 1, and then 3 factorial is 6. So I had negative, positive, and of course this would continue, and the next term would end up giving me a negative value. And that is because this general term included -1 to the n plus 1, that I could see by looking at the general term that these numbers that were added together were going to alternate. So no two have the same sign, right? They're not both positive, positive, or negative, negative. They switch every other term. So now here I have n equals 0 to infinity of -3 to the n, so let's write out a few terms. So -3 to the 0, plus -3 to the 1, plus -3 squared, and then plus -3 cubed. And we'll just keep putting dot, dot, dot. So anything to the 0 is 1. -3 to the 1, so this is plus -3. Plus -3 squared, so the negative is in the parentheses, so the negative is being squared away, so we're going to get positive 9. And then -3 cubed, so I'm raising a negative to an odd number, I will get a negative value out, so plus -27, and then so on and so forth. So I have positive 1 plus -3 plus positive 9 plus -27, so my terms are alternating. Now, I don't in general see the -1 to the n or the -1 to the n plus 1, but I could have rewritten this series to be n equals 0 to infinity of -1 to the n, 3 to the n. So this is another way that I could have written this series out so that I could explicitly see the -1 to the n part that will make my series alternate in sign. But then finally, let's take a look at this last one. So the sum from n equals 0 to infinity of cosine n pi over n squared plus 1. So we will go ahead and write a few terms out in the series. So starting with 0, I'm going to have cosine of 0 times pi, so that's 0, over, if I plug in 0, 0 squared plus 1 is going to give me 1. Plus, now I have to plug in 1, so I have cosine of pi over, so if I plug in 1, 1 squared is 1 plus 1 is 2, plus, so now I have to plug in 2, so I have cosine of 2 pi over, if I plug in 2, 2 squared is 4 plus 1 is 5, and we'll do one more, cosine of 3 pi, and if I plug in 3, 3 squared is 9 plus 1 is 10. So now it's a matter of evaluating cosine at different angle measures in radians. So cosine of 0 is 1, so this is 1 over 1, plus, well, cosine of pi, so just to draw a quick unit circle, so over here, here's pi, this coordinate point is negative 1, 0, cosine is the x value, so negative 1 is cosine of pi, so this is negative 1 over 2, plus cosine of 2 pi, so 0 is 2 pi, which we just said was 1, so this is 1 over 5, plus cosine of 3 pi, well, pi is the same as 3 pi, so I'm going to end up getting cosine of 3 pi to be a negative 1 over 10. So we had a positive plus a negative plus a positive plus a negative, and so this is going to continue to alternate. So you can see that cosine n pi is another part of a general term that will make the terms in the series alternate in sign. So negative 1 to the n plus 1, negative 1 to the n, both of those will work and they are obvious, but cosine n pi wasn't quite as obvious, but you can see that it will make the terms in the infinite series alternate as well. So alternating term series test for convergence. So let's suppose I have the sum of a sub n as a series with a sub n strictly alternating. We can use the following tests to determine convergence of that alternating term series. We can use the alternating series tests, we can use the geometric series test, we can use the ratio test, and we can use the root test. The alternating series test. If a sub n is positive, then the series, the sum of negative 1 to the n times a sub n, or any equivalent alternating series, converges if the limit as n approaches infinity of a sub n equals 0, and if a sub n plus 1 is less than a sub n for all n, at least past some particular value big N. So informally, here's what the alternating series test says, that a series converges if all three parts of this are satisfied. If number 1, the terms strictly alternate in sign. If number 2, the individual terms decrease in magnitude, meaning decrease in size. So we want the numbers to be getting smaller as I move along the sequence of terms that's being added together. But we don't care about their signs because they're alternating in sign. So it's just the terms without their signs are getting smaller. And if the terms tend to 0. So it's like performing the nth term test. So the nth term test says that the general term has to go to 0. So here's the biggest warning here, is that the alternating series test cannot ever be used to show divergence. So if this portion fails, if the limit as n approaches infinity of a sub n does not equal 0, we must say that the series diverges by the nth term test. So in other words, we can never say the statement that this series diverges by the alternating series test. So the alternating series test is a convergence test only. Alright, in these examples we want to use the alternating series test to determine if the following converge. So we have the sum from n equals 0 to infinity of negative 1 to the n plus 1 over n factorial. So what I'm going to do is I'm going to write out 1, 2, and 3. I wanted to make sure that I satisfy 3 different components. Now, the first component is this series alternating? So, alternating, question mark? Yes, we know the series is alternating because it includes an alternating term, negative 1 to the n plus 1. So, yes, this is alternating. The second part said that I wanted my series to decrease in magnitude. So, in other words, let's write out a few of the terms in this particular sequence, but not including the alternating part. So we're just looking at, let's say this was negative 1 to the n plus 1 times 1 over n factorial. So we're concerned with just the a sub n part, so not the part that alternates. And we're looking at whether these individual terms are getting smaller. So in other words, 1 over 1 factorial, that's going to be, or 0 factorial, sorry, 0 is the first one I'm plugging in, so that's still 1 over 1, so that's the first term. And then the next term, so I'm just looking at the individual terms in the sequence that I'd be adding together. Then if I plug in 1, I'm still going to have 1. So from one to the next, I'm not getting smaller, I'm not decreasing in magnitude, but let's keep going. So now if I plug in 2, 2 factorial is 2, so I get 1/2. 3 factorial is 6, so I get 1/6. Then 1 over 24, and then 1 over 120. So these are all the terms I'm adding together. Of course, they would alternate in sign, but we're just looking for whether or not these terms are going to get smaller at some point. Well, if we just compared the first two, they're not decreasing. But remember, there's that whole idea of past a certain point, the numbers have to be getting smaller. Well, past those first two terms, now the numbers are finally starting to get smaller. So decrease in magnitude, yes, this is true. So that formally was written as a sub n plus 1 is greater, or I'm sorry, not greater than, is less than a sub n. So the next term is always going to be smaller than the previous one, in other words. So that is happening in this example. And then number 3, we want to make sure that the limit as n approaches infinity of a sub n, the general term without the alternating part, 1 over n factorial, we want to make sure that this goes to 0. Now, if n approaches infinity, this denominator is getting huge, so this is going to 0. So yes, all 3 parts are satisfied. So by the alternating series test, we can say that the series converges. Alright, so now let's try the next one. I have the sum from n equals 0 to infinity of negative 3 to the n. So we can think about this as the sum from n equals 0 to infinity of negative 1 to the n, 3 to the n. Just so we could really prove to ourselves that this is alternating. It does have an alternating part to the general term. So 1, alternating, yes. And then 2, do each of the individual terms decrease in magnitude? So here we're looking at this a sub n portion. And if I start to substitute in 0, so 3 to the 0 is 1. And then if I substitute 1 into this general term, I'll get 3. 2, I'll get 9. 3, I'll get 27. And so on. So these individual terms are getting bigger. This is going to infinity. So these individual terms are not decreasing in magnitude, so I fail this portion here. But here's the warning, is that I cannot say that this series diverges by the alternating series test. The part that it's diverging truly by is the nth term test, because if I do the limit as n approaches infinity of this general term, 3 to the n, as this exponent goes to infinity, this whole quantity is going to infinity. So here is where I would say by the nth term test, the series diverges. So even though, yes, I did fail the second part to the alternating series test, I would never want to say that I diverge by the alternating series test. I have to show that instead the limit of the general term is non-zero, right? This does not equal 0. So by the nth term test, we have that this infinite series diverges. And of course, just as a side note, if you were thinking this is a geometric series test, yes, it absolutely is geometric, and the absolute value of r is greater than 1, so it diverges. So we can also say that this series diverges by the geometric series test. It's just in this example, we were trying to talk about the alternating series test, but in general, we could use the nth term test to determine divergence, or the geometric series test will allow us to determine divergence. So now we have the sum of n equals 0 to infinity of cosine of n pi over n squared plus 1. In a previous example, we found that cosine n pi is going to make our terms alternate. So portion 1, is this an alternating series? Yes, it is, because of the cosine n pi part is going to make the numerator alternate in sign. So that means that the general term a sub n, so I'm just going to write that down here, is 1 over n squared plus 1. So the second thing we have to check is that individually each of these terms is getting smaller and smaller. So as I substitute in 0, I'm going to get a 1 over 1. And then as I substitute, as I substitute in 0, right, 1 over 1, 1, I'm going to get 1 over 2. 2 squared is 4 plus 1 is 5. So 1 over 5, and we'll do one more, 3. 3 squared is 9, plus 1 is 10, so I'm going to get 1 over 10. So each of these terms individually is getting smaller, so I have a sub n plus 1 is less than a sub n. The next term is less than or equal to the previous term, so that works out. And then we have to check that the limit as n approaches infinity of the general term without the alternating part, 1 over n squared plus 1, converges to 0. And as n approaches infinity, the denominator is getting bigger faster, so this is true. So by the alternating series test, we have that the series converges. And now let's take a look at this one. I have the sum of n equals 1 to infinity of negative 1 to the n over the square root of n. Now here a lot of students are tempted to say that this is a p-series, but it is not. A p-series requires me to have a 1 in the numerator, or at least some constant that I could pull out of the summation. But here I cannot pull out this negative 1 to the n, so this is not a p-series, but it is an alternating series, so I'm going to use the alternating series test. So alternating, yes it is. It has this negative 1 to the n term. 2, the general term, so my a sub n is 1 over the square root of n. So we have to decide if these terms are getting smaller one by one. So I'm going to have 1 over 1, 1 over rad 2, 1 over rad 3, and so on. So yes, we have a sub n plus 1 is less than or equal to a sub n. And then finally, part 3, we need to show that the limit as n approaches infinity of 1 over radical n is going to go to 0. And again, as I approach infinity, the denominator is growing faster than my constant on the top 1, so this is 0. So we can say by the alternating series test that this series does converge. So in this last example, I have the sum of n equals 2 to infinity of negative 1 to the n times n over n plus 1. So we can see at first that it is an alternating series. So I have negative 1 to the n as part of the general term. And for the second part, to determine if the general term without the alternating portion decreases in magnitude, I'll start by plugging in my index 2. So my numbers are going to be 2 over 3, and then 3 over 4, 4 over 5, and so on. And hopefully we can see, if we want to think about it in a decimal notation, this is 0.6 repeating, this is 0.75, this one's 0.8, so these are not getting smaller in magnitude, so this portion of the alternating series test fails, but we'd really have to say that the limit as n approaches infinity of n over n plus 1, well, that does not equal 0, and so we have to state that this diverges because of the nth term test. So remember, we cannot state divergence from the alternating series test.